Welcome everyone to our OpenSim webinar. There's a great turnout this morning or afternoon, depending on where you're calling in, joining us from. So my name is Jennifer Hicks. I'm the OpenSim R&D Manager and the Associate Director of our National Center for Simulation and Rehab Research. I'll be serving as the moderator for the webinar today. I'm pleased to welcome today's presenters. Kevin Shelburne, Alessandro Navacchia, and Azhar Ali are joining us from the University of Denver. They'll be presenting on musculoskeletal simulations that combine multiscale data and finite element modeling of the knee. Next slide. So a little bit about OpenSim before we get started in case you're new to the project. So OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating movements of humans and animals. So the first goal of our webinar series is to showcase many of the cutting-edge research projects that are being conducted with OpenSim. OpenSim is also a large and geographically diverse community of users. So the second goal of our webinar series is to provide a platform so that all of you, the members of the OpenSim community, can communicate and collaborate. Next slide. So before we get started, I have a few quick reminders about the format of the webinar. We definitely want to leave time to answer your questions, but we'll do those at the end of the presentation using the WebEx Q&A interface. If you need any additional technical help, you can consult the guide on our website. Next slide. So now let's get going. I want to introduce our speakers. So first, Kevin Shelburne. Dr. Shelburne received his PhD from the University of Texas, and he worked for Lockheed Martin Space Systems until joining the Biomechanics Research Lab at the Steadman Hawkins Research Foundation as Assistant Director. And in 2010, he began work as a Senior Research Scientist at the University of Denver in the Department of Mechanical and Materials Engineering, where he's now a Research Professor in the Center for Orthopedic Biomechanics. Alessandro Navacchia is our second speaker for today. He recently completed his PhD in Mechanical Engineering at the University of Denver, focusing his research on multiscale musculoskeletal modeling, and he's currently a postdoctoral fellow at the Center for Orthopedic Biomechanics. And then third, we have Azhar Ali. Mr. Ali is currently a PhD candidate in mechanical engineering at the University of Denver, also in the Center for Orthopedic Biomechanics. And his research is focused on musculoskeletal and finite element modeling that addresses clinical issues in joint replacement. So thank you guys for joining our webinar series. We're really excited to hear more about your work. And with that, I'll let you take it away.
Thank you, Jen. Hello, everyone. This is Kevin Shelburne. Thanks very much for joining us. We also thank Joy and Jen for arranging the webinar and hosting. Today, we'll be discussing what we call the sequential multiscale modeling using OpenSim as input to finite element models of the knee. I'll provide a short introduction, then Alessandro Navacchia and Azhar Ali will describe two examples from their recent work using this approach, focused in the study of knee joint replacement. In a few minutes, I'll introduce these examples more fully, but I want to start with some context. The three of us, as Jen said, work in the Center for Orthopedic Biomechanics at the University of Denver. Our center is located in the Department of Mechanical and Materials Engineering and the New Ritchie School of Engineering and Computer Science that's pictured on the right. To save time, I won't introduce each of the people listed here. We're all part of the center, but what I really want to communicate most of all is that the work of the center is strongly collaborative. Although the three of us are presenting today, many of the ideas and development comes from us working together as a team. And we do this through 4 collaborative laboratories and specialties. And we work on a broad range of projects that move across these laboratories, and many of which utilize musculoskeletal modeling with OpenSim. One of our primary areas of research in the center is joint replacement. So bringing the focus back to modeling joint replacement of the knee and our motivation for doing so. More than 600,000 total knee replacements are performed in the United States each year, and this number is continuing to grow. It's a very successful surgery with something like 95% of patients having a good or excellent outcome. But unfortunately, many patients continue to exhibit long-term adaptations in their movement patterns that might be attributed to quadriceps muscle deficits or compensation for knee instability or knee stiffness or pain. And this might be caused by changes in their limb alignment or implant geometry or poor physical therapy or some combination of these. In short, patients are surviving, but not all of them are thriving. So how do we improve? There's a number of ways to improve, but we think one way might be through better evaluation and understanding of clinical outcome. We can measure patient function in the gait laboratory, and from the recorded marker positions and ground forces, we can use OpenSim to calculate the joint angles and joint moments, muscle and joint forces associated with these movement compensations that are describing the deficits that these patients suffer from. But we also need to understand how these characteristics impact the knee, the contact forces, contact location, strains in the tissues. And ultimately, we want to be able to ask what if sorts of questions, such as what if the implant had been placed differently, or what if certain muscles were stronger or weaker, and then how would that influence the patient's function or the survival of the components. One of the challenges is that musculoskeletal models, including OpenSim, are based on rigid body dynamics and lack some of the subject specificity and deformable realism at the smaller scale of the knee. So in our joint representations, we use deformable finite element models because we can model complex geometries such as subject-specific articular and tissue geometry. We can assign subject-specific material properties and then use these models to estimate stresses and strains in soft tissues, bones, implants. The challenge is here that if you have a model of the joint like this, it requires an applied loading condition or kinematics as input from some other source. Another challenge is that these models can be much more computationally expensive, which makes it hard to build whole body musculoskeletal simulations like you see in OpenSim. One more thing about detailed joint models is that require calibration and validation. This can be achieved through simulation of in vitro experiments like is pictured here. In the video, a knee specimen in the Kansas knee simulator is on the left. This is in Lauren Maletsky's lab at KU. And on the right is a finite element simulation of the same experiment. So in these experiments, everything you need is available: tissue geometry, kinematics, and loads, and calibrate soft tissue response in the model and verify the accuracy of the joint models. So to address some of the limitations of these two approaches of OpenSim and finite element modeling, we've combined them into a sequential multi-scale modeling approach. A musculoskeletal model at the whole body scale in OpenSim is used to estimate a loading condition, muscle or joint forces that are then applied to the detailed finite element model of the knee to estimate tissue and component deformation. One thing is that for this multi-scale approach to work well, we also need multi-scale data from patients. Predictions at the knee can be improved if we have accurate joint kinematics for input. So for this, we've been using stereoradiography to collect accurate movement of the knee at the millimeter scale. This is, of course, images of a hip replacement data collection, but it's a good set of images to show the setup. Stereoradiography uses two synchronized X-ray systems that produce dynamic images or X-ray movies for tracking bone and implant movement. The stereoradiography system is then synchronized with whole body motion capture and recording of ground forces, all of these captured simultaneously. This way we have data for input at the scales of the sequential approach. We have body segment motion and ground forces for input to OpenSim, as well as small scale kinematics for input to the knee joint level and scale of the model. So with this approach, we have, coming back to this slide, multiscale data for input to sequential models of the body and knee that provide a multiscale portrait of patient function with reasonable computational efficiency, because we have all the outputs from OpenSim, as well as the deformable representation of the knee. Eventually, we want to blend these models into a single model approach, because in reality, what happens at the knee affects muscle forces. And you'll see the beginnings of this blending of models and data in the examples that we'll present. And we'll revisit this single model idea briefly at the end of the talk. The two examples we'll describe today demonstrate use of OpenSim with FE modeling for research in knee joint replacement, and to provide something of a roadmap to the examples. In the first example presented by Alessandro, he used this approach to predict muscle forces and contact between the components of the tibia and femur, inputs to the finite element model or joint loads from OpenSim, and tibiofemoral kinematics from the radiography system. This was our first study using this approach. We will also discuss a follow-up advancement from this study using radiography data to prescribe knee motion in OpenSim as well. And then next, in the next example, in a more recent study presented by AZ, there are further advances in the approach. He used both tibiofemoral and patellofemoral kinematics from radiography as inputs to the finite element representation he built. And the FE model in this case includes both muscle and soft tissue, not just the components. And so rather than joint loads being input to the FE model from OpenSim, the inputs are muscle forces. So with that, I'll turn it over to Alessandro to begin example one.
Thanks, Kevin. Hi, everybody. This is Alessandro, and the title of the first example of the multiscale sequential approach that I'm presenting is subject-specific modeling of muscle force and knee contact in total knee arthroplasty. So the goal of this study was to estimate subject-specific contact mechanics for 6 patients implanted with a cruciate retaining total knee arthroplasty, performing 3 activities: gait, stair descent, and chair rise. The experimental data for this study were collected at the Institute for Biomechanics at the ETH in Zurich. This lab is run by Dr. Renate List. And specifically, motion capture data, ground reaction forces, EMG, and movable fluoroscopy images at the implanted knee were simultaneously collected. Here we can see a quick video of a subject performing a stair descent activity, and you can notice that the movable fluoroscopy system automatically follows the implanted knee of the subject. So after data collection, the second step of our sequential workflow is to estimate joint contact loads at the implanted knee with a whole body musculoskeletal model in OpenSim. The model that we used was based on a previous model presented by Delp et al. And just few changes were made for this study. First of all, the quadriceps mechanism was added to the model, and the quadriceps muscles were directly attached to the tibial tuberosity, passing through the tibia, through the patella. And this was done to improve quadriceps moment arms and also to correctly transfer the quadriceps loads to the tibia. The second change was that the gastrocnemius muscle was taken from a different model presented by Arnold et al. And this was done because the moment arms of this muscle model are more consistent with cadaveric measurements from the literature. So in OpenSim, we performed a series of analyses with the final objective of estimating joint contact loads at the implanted knee. This sequence that I will describe is a pipeline that is commonly used in OpenSim to go from data collected in the lab to muscle and joint force predictions. So the first analysis was an inverse kinematics analysis. The input for this analysis is motion capture market data, and it allows to estimate joint angles. These joint angles, together with ground reaction forces measured in the lab, were used to perform an inverse dynamics analysis that allows to estimate the joint moments needed to perform a specific activity. Then a muscle force optimization, specifically a static optimization, was performed to find a unique combination of muscle forces that minimizes the sum of the muscle activations squared at each simulation time frame. You can see the objective function of the optimization on the left, and muscle forces are the output of this analysis. And finally, these muscle forces were used as an input to joint reaction analysis to estimate the contact loads at the implanted knee. In particular, we were interested in the compressive load and the varus valgus contact moment on the implant. And so the third and final step of our sequential approach was a finite element simulation of the subject-specific implant to correctly estimate contact mechanics. The boundary conditions for this finite element simulation were a combination of kinematic measurements from fluoroscopy images and joint loads estimated with the musculoskeletal model. Specifically, the flexion extension rotation, internal external rotation, and anterior posterior translation were directly driven in the simulation from kinematic measurements, and the compressive load and the varus valgus contact moment estimated from the OpenSim simulations were applied in those 2 degrees of freedom. So to summarize the method implemented in this sequential approach, results from the OpenSim joint reaction analysis and from fluoroscopy kinematics were used as inputs to a finite element simulation performed in Abacus. So Abacus is the finite element framework that we use here at the University of Denver. And this interface between the 2 inputs and the finite element simulation consisted of custom MATLAB scripts that also take advantage of the OpenSim MATLAB API. Just to quickly show you an example of what we did, this is an output data produced by the joint reaction analysis performed in OpenSim. It is a storage file, and it presents the joint loads, the big matrix, as a function of time. You can see the time column on the left and the joint loads in the matrix. And this data was converted with our MATLAB scripts into Abacus input files that are simply text files in which we can find, again, the time column on the left and the actual joint loads on the right. So here we can look at 4 videos of our simulations for a gait cycle, the musculoskeletal model on the top left, the fluoroscopy images in the top right corner, and the finite element simulations on the bottom that estimated the subject-specific contact mechanics. And so to gain more confidence in our joint load results from OpenSim, we compare them to experimental data from telemetric implants for the 3 activities. Here we can see in the figure on the left that our results, shown in blue, compare favorably with the experimental data from the literature that are shown in black. And a more complete validation of our musculoskeletal model results can be found in the journal publication prediction of in vivo knee joint loads using a global probabilistic analysis. And as I mentioned, the final objective of the study was to estimate subject-specific and activity-specific contact mechanics. I will not present in this presentation the details about our results, but I just want to stress the fact that a detailed deformable finite element simulation like the one that we implemented in this study can provide several significant results, such as center of pressure, contact area, contact pressure, local stresses and strains, and for example also micromotion between the insert and the tibial tray. For a more complete set of results, I refer you to this other publication that is subject-specific modeling of muscle force and knee contact in total knee arthroplasty. So, as Kevin mentioned in the introduction, the main limitation of this study is that the 3D tibiofemoral kinematics from fluoroscopy images was only used as an input to the finite element simulation, but it was not implemented into the knee joint of the OpenSim musculoskeletal model. And so now I try to explain how this limitation can be addressed and why it is important. So first of all, I have to define what a muscle moment arm is. A muscle moment arm is defined as the effectiveness with which a contraction force generates a moment at a joint of interest. In a more mathematical form, we can see that the moment arm R maps the force of a specific muscle into the joint torque tau that the muscle force can generate. As I mentioned before, when I was describing the OpenSim pipeline we used to estimate joint loads, the joint moments obtained from the inverse dynamics analysis are the input to the muscle force optimization. And therefore, we can immediately see that the muscle moment arms have a substantial influence on muscle force prediction because they map the muscle forces into those joint torques that are needed to perform a specific activity. The moment arms are determined by mainly two factors: the geometry of the muscle, so how well we are able to represent the path of the muscle, and also joint kinematics. However, the joint kinematics that is often implemented in whole body musculoskeletal models consists of average passive cadaveric motion. That may not be representative of what really happens in the knee joint in vivo. And therefore, we decided to quantify the influence of in vivo kinematics on moment arms. And to do so, we implemented the 3D subject-specific and activity-specific kinematics from fluoroscopy into an OpenSim model in order to obtain personalized muscle moment arms. The 3D tibiofemoral kinematics can be described as a 4x4 transformation matrix. And this matrix can be parameterized in a sequence of 3 Cardan angles and 3 translations. And the degrees of freedom of the knee, and I mean the 2 rotations, internal and external rotation, varus valgus rotation, and the 3 translations, can be described as a function of the knee flexion angle, that is the primary degree of freedom of the joint. And these functions of the knee flexion angle can be easily defined in OpenSim as OpenSim splines, and they can be prescribed into the joint model of the musculoskeletal model. And this process allowed to implement, again, the subject and activity-specific kinematics to replace the average passive cadaveric motion. And the results that we observed showed that in vivo kinematics actually has a substantial influence on moment arms. And I refer you to the following publication for more details on our results. And the title of the publication is Dependence of Muscle Moment Arms on In Vivo 3-Dimensional Kinematics of the Knee. So to summarize, I presented this final piece about muscle moment arms to explain that implementing multiscale data into the musculoskeletal simulation can improve the muscle force and joint load predictions. And This was done by AZ in the second example of our sequential approach that he will present now. So I pass it to AZ for the second example.
Thank you, Alessandro. Hello, everyone. My name is AZ, and I will describe the second example to the sequential approach described by Alessandro. This study expands the OpenSim and finite element framework by including subject-specific patellofemoral kinematics from the radiography system and description of muscle and patellofemoral soft tissue representation within the finite element analysis. An important finding from Alessandro's previous work was that muscle moment arm predictions from OpenSim are significantly influenced by the subject-specific kinematics. It is then important to include subject-specific motion in OpenSim when using OpenSim to predict muscle forces, as I will do in this study. My study applies the sequential OpenSim and finite element modeling approach to evaluation of in vivo mechanics for medialized dome and anatomic patellofemoral geometries during knee extension and lunge. And so I'll provide some general background to this study. As most of you already know, total knee arthroplasty has in general been a successful solution for osteoarthritic patients, but there's demand for higher knee function post-TKA. Patients have shown evidence of reduced range of motion, quadriceps strength, and extensor efficiency. The design of the patellar component plays an important role in anterior knee pain through tissue strain due to unnatural kinematics. The resurfaced patella can also change the effective moment arm of the patella, which can impact patient strength and quadriceps efficiency. And so the objective of the study was to develop a pipeline for evaluation of in vivo patellofemoral mechanics and compare the impact of the medialized dome and anatomic designs on the joint mechanics. And so the workflow for this study includes data collections from the Human Dynamics Lab at the University of Denver for 20 attuned posterior stabilized rotating platform subjects, 10 with the medialized dome patella geometry, and 10 with the anatomic patellar component during a seated knee extension and lunge activity. This workflow is similar to the methods described by Alessandro, except for some additions that I will highlight in greater detail. And so data collections include the stereoradiography system, whole body motion capture, ground reaction forces, and EMG. Tracking was performed by registering the 3D patella bone and femoral and tibial implant geometries to the 2D radiography images. Tracking returns the relative tibiofemoral and patellofemoral joint kinematics for each activity. Whole body motion capture, ground reaction force data, and kinematics from the stereoradiography system are input into subject and activity-specific musculoskeletal models to predict muscle forces. The inclusion of radiography-based patellofemoral kinematics into the OpenSim framework is an additional level of complexity in this study, but it's necessary for implementation of more accurate muscle moment arms. The subject-specific joint kinematics and quadriceps force predictions from OpenSim are then input into finite element analyses to simulate knee extension and lunge activities and predict the patellofemoral mechanics. The following figures show the mean plus or minus 1 standard deviation of patellatibial sagittal plane tilt from the stereoradiography system for anatomic subjects, which are represented in purple, and dome subjects, which are represented in orange. Kinematics for the two patellar designs are also compared to an age-matched group of 8 healthy natural subjects that were also collected and tracked in the lab. It's important to note that load-bearing activities such as lunge highlighted differences in the kinematics between the two designs. Also, anatomic subjects demonstrated trends in patellar flexion closer to that of natural subjects. Dome subjects demonstrated significantly larger patellar flexion than anatomic subjects, with an average difference of 11 degrees from 40 to 100 degrees of knee flexion, and up to 15 degrees difference at 90 degrees knee flexion. These differences in patellar flexion between anatomic and dome subjects were consistent with our previous cadaveric work, but I'm interested in evaluating how these differences impact the patellofemoral mechanics. And so to investigate the mechanics, I used OpenSim to predict quadriceps forces for each subject. Again, motion capture, force plate data, and subject-specific joint kinematics from the stereoradiography system were used in subject and activity-specific musculoskeletal models to predict quadriceps forces. The OpenSim models were based on the same generic model used by Alessandro, including the quadriceps mechanism attached to the tibia, and also including the splines describing the subject-specific tibiofemoral and patellofemoral kinematics from the experiment, which in turn affected the muscle moment arms and quadriceps forces. Predictions of quadriceps forces for anatomic and dome subjects were very similar in the knee extension task, but there were significant differences during lunge, with anatomic subjects demonstrating higher quadriceps forces in deep flexion. Dome subjects may have demonstrated lower quadriceps loads due to compensation for quadriceps weakness. I noticed subjects would tend to offload the quadriceps by leaning on the contralateral limb. There was significant variability in quadriceps forces for dome subjects. OpenSim predictions were able to capture the unique strategies in the performance of the task. We have used in vitro cadaveric work to support the development of the finite element representations for the bone and soft tissue. For this study, we used prior in vitro experiments and modeling of a deep knee bend to support our representation of the quadriceps mechanism. Previously validated models provide confidence that our finite element representations have the necessary complexity to replicate the experimental patellofemoral motion and mechanics. This supplemental work has been published in the Journal of Biomechanics. And so I've applied what I learned from the cadaveric work to modeling in vivo mechanics of the implanted knee in this study. One of the key advancements from Alessandro's work is the inclusion of muscle and soft tissue in the finite element analysis. The finite element model includes the femoral and tibial tray and insert components, the patellar bone virtually implanted with the patellar component, and patellofemoral soft tissue structures including the rectus femoris and basti tendons and the patellar ligament, which are modeled using 2D fiber-reinforced membrane elements. Medial and lateral patellofemoral ligaments are modeled using 1D nonlinear tension element springs, and a quadriceps muscle line of action is defined based on a muscle centroid path from the Visible Human project. The boundary and loading conditions of the finite element model include 6 degrees of freedom tibiofemoral kinematics that are prescribed based on the experimental data, and the patellofemoral joint was free to move, and quadriceps force was applied based on predictions from OpenSim. Models were calibrated to match the experimental patellofemoral kinematics, including perturbations of the patellofemoral soft tissue attachments and initial pre-strain in the medial and lateral patellofemoral ligaments. The figures on the right show the calibration of a representative subject. Finite element models were used to predict the patellofemoral mechanics and quadriceps efficiency measures, including moment arm patellar tendon angle and load distribution between the patellar tendon contact and quadriceps force. The following are predictions of moment arm from the finite element simulations. Patellar tendon moment arm was measured as the perpendicular distance between the knee joint center and the patellar tendon. Anatomic subjects had a higher moment arm in early flexion in comparison to dome subjects. Both implant designs demonstrated relatively small moment arms when compared to natural data in the literature. I also measured the ratio of patellar tendon load and contact force to quadriceps force. The distribution of loads surrounding the patella are important metrics for evaluating the performance of the patellar component design. Finite element analysis allows the measurement of the soft tissue and contact mechanics that are otherwise difficult to measure from OpenSim alone. The results shown here are for the lunge activity, which demonstrated greater differences between the two designs. The patellar force ratio is shown on top, which is the ratio of patellar tendon force to quadriceps force. Higher efficiency is represented by values closer to 1, since more load is being transferred from the quadriceps to the patellar tendon. Anatomic subjects demonstrated a higher quadriceps efficiency at deeper flexion angles greater than 75 degrees. The ratio of contact force to quadriceps force is shown on the bottom. Dome subjects demonstrated higher contact forces than anatomic subjects with significantly higher contact loads in deep flexion. And so the main takeaways from this study were that anatomic subjects demonstrated patellar flexion closer to that of the natural subjects, which was consistent with previous findings. Also, anatomic subjects demonstrated improved moment arm, quadriceps efficiency, and lower contact forces, which could indicate better performance. Results indicated significant patient variability in the kinematics and mechanics, highlighting the need for subject-specific modeling. The addition of radiography-based patellofemoral kinematics in the OpenSim and finite element framework was significant in that it distinguished important design characteristics between the two implant designs. I'll pass it back to Kevin for some closing remarks.
Thanks, Daisy. So I hope that we've convinced you of the utility of using this multiscale sequential approach and the importance of including multiscale data. Bringing back this figure from the introduction, as you've seen, the OpenSim and finite element models really target two scales. But in Alessandro and Nazi's work, some data, such as the radiography data, is used as input in both models, and some of the tissues, such as the quadriceps and the patellar model, is represented in both models as well. But even with this overlap of data and models, this approach has some inconsistency, because in reality, ligament and contact forces predicted at the knee will affect muscle force estimates if they were included in the OpenSim model. Many researchers, including us, are working on combining these models because in real tissue there's no separation of scale. So for us, using OpenSim as a guide, we're doing this by increasing the realism and completeness of the finite element model to preserve the interactions between the whole body function, the muscle force, and joint level mechanics. Our long-term objective is to create one multi-scale model that combines a realistic model of the knee with a complete model of the body segments and muscles. In closing, the Center of Orthopedic Biomechanics thrives because of collaborations and generous support from our research partners. We would like to thank the NIH, NSF, and DePuy Sensies for their support. In addition, we want to thank our collaborator facilities and colleagues at the University of Kansas, ETH, and Zurich, our clinical partners at Colorado Joint Replacement, and colleagues at University of Colorado. We want to thank also our alumni from the Center for Orthopedic Biomechanics, Claire Fitzpatrick, Mike Harris, and Adam Sear. And also want to thank our research assistants who make this work possible. Thank you, and please visit our sites on simtk.org. There you'll find links to models, in addition to much of the data that goes into building our models. If there's some data you don't see there that you might need, let us know, and we might just be able to provide it for you. So thanks again, everyone.
Thanks, Kevin, Alessandro, and AZ for a really great talk, and thank you also for sharing your models and data and tools. That really helps the whole field move forward, so thank you for making those contributions. Now we'd like to go ahead and open up for questions from the audience. So as I mentioned at the beginning, the questions will be text-based, so go to the Q&A button on your WebEx interface and type your question. Make sure you select to ask your question to all panelists. We already have one question that came in from the audience. This is from Hossein Maztarzadeh. Sorry for the mispronunciation there, I'm sure. First, he says, thank you for the nice work. And his question is, where do you apply OpenSim joint loading in your FE model?
So yeah, I guess he's referring to the first example that I presented. This is Alessandro, and we basically in the finite element model we recreated a Gruden-Santi representation of the knee joint, and we applied those joint. After transforming those joint loads from OpenSim to a Gruden-Santi notation, we applied them to the axis of that Gruden-Santi representation in the finite element model. I hope this is clear. Obviously, there are some technicalities when you go from OpenSim to Abacus. I tried to explain as well as I could how the input files look like, the input files for the Abacus simulations. But yeah, this is what we did.
Oh, okay. So Amit Iyengar has a somewhat related follow-up question. So then, how is the joint in OpenSim reconciled with the contact locations from the FE model?
Yeah. So we made sure when we converted our joint loads from OpenSim into the finite element simulations, we made sure that the local coordinate system of the knee joint in OpenSim was located and oriented the same way as the coordinate system in our finite element simulations, so that we were consistent. And so the contact location that we got and the contact mechanics that we got from a finite element simulation were also consistent with the local coordinate system of the knee joint.
I think an additional challenge with that and with using the radiography data is that we have to resolve the coordinate system from the radiography data collections too, so they all have to match.
Okay, great, thank you. Now a question from Mohammed Hussein. He says, thanks for the amazing talk. And he's asking, did you perform any finite element analysis from ANSYS workbench as well?
We didn't, but I think much of the input files that we use in Abacus could be transformed into and used in ANSYS.
Great, thanks. So lots of questions coming in. Now we have one from Jingwen Hu. So he or she says, thanks so much for your interesting presentation. As of now, how long does it take to build a patient-specific model in OpenSim and with the patient-specific finite element knee model?
You want to say how long each of yours took?
Sure.
Yeah.
Yeah. So the OpenSim model, it doesn't take long because we start from the generic model that is the same for every patient, and we scale it to the dimensions of the subject, of the specific subject, and therefore the scaling process is maybe it's a little time consuming because you have to figure out. You have to make sure that that after the scaling, your model is actually consistent with your experimental data. But all the OpenSim pipeline is very quick, actually. So, like for example, the most time-consuming process is the static optimization, and it takes like 1 minute for a gauge cycle activity. But building the model is fairly quick since we start from a generic model. Then the finite element model that I implemented for my first example was also very simple to create because it only included the meshes for the 3 implant components, so the femoral component, the insert, and the tibial component, and it was just a matter of positioning and aligning it to the local coordinate system of the knee in OpenSim. And to run the actual simulation with a deformable insert, it takes about 6 or 7 hours for like a gauge cycle activity from his strike to his strike. So it is obviously more computationally expensive than the OpenSim simulations.
Yeah, and this is AZ. In addition to the time described by Alessandro, at least for my work within the finite element simulations that contained muscle and patellofemoral soft tissue, the calibration of the patellofemoral soft tissue is an added element, as we wanted to try and include as much personalization within the model in order to match the experimental patellofemoral motion from the stereoradiography data. We adjust the alignment of the patellar ligament to try and match the experimental patellofemoral motion, and that can be time consuming and take a few days to match that motion. The tracking element of creating the model as in processing the experimental data can also be a time consuming process and take a few hours to create, go from the stereoradiography data to tibiofemoral and patellofemoral kinematics.
Great. So that question is actually a good lead-in to a question I had. So you mentioned that subject variability was important in the results that you saw as far as joint loading. So I was wondering what you think is the best way to take these kinds of models toward having an impact on clinical decision making. Do you think the goal is to try to make these subject-specific models, fast enough and easy enough to use that they could be used for specific patients, or do you think that there are some key factors about patients that put them into specific groups, or a couple key measures that we could make to help choose which implant to use and how to implant it?
Yeah, I'll be interested to see what these guys think as well, but I think the eventual goal is to try to make these tools much more clinically applicable. There's definitely more work that has to happen here, of course, to make things happen more quickly. But I think one of the things that became clear, or becomes clear when working with patients, both in the laboratory as well as trying to model them, is that people are very unique, and that patient-specific results are important for, just as you say, for we think eventually determining what kinds of implants should be applied to certain people. Right now, we're more interested in using these tools in, for instance, that design phase and trying to better understand the deficits that people with joint replacement have, so that we can better improve the surgery or the physical therapy.
Cool. Yeah, that makes sense. And we're interested in clinical impact here in the Stanford team. So if there's anything we can do to help on the OpenSim software side, do let us know as well.
That'd be great.
Yeah. So we have lots more questions actually. So let's I'll dive into those. So now a question from Sali Asma. Thank you for this work. Did you look at patellofemoral contact stresses using the FE model? And if you did, how do they change based on the activity-specific model?
You repeat the last part of the question?
So did you look at patellofemoral contact stresses using the FE model? And then I think the question is whether they changed based on activity or based on the different implant types.
Yeah, so in that last part of Daisy, I did look at the patellofemoral contact stresses, and they generally, the contact stress increase for the lunge activity, which carried more load, and also the location of it increased as a function of flexion. But generally, their location and position was activity independent.
Okay, great, thanks. Now a question from Michael Owens. So have any of your test subjects required a revision? And if so, have you considered working with the Retrieval Lab and using this technique as part of a failure modes analysis?
For these studies, these were people that were high functioning, which is interesting, but also because they still had challenges. One of our plans is to work with revision patients. And working with our local clinical partners, our plan is to bring in folks pre-revision for measurement and analysis. And here at the U, we've begun a new retrieval laboratory, so that what we propose to do is bring in people for measurement and analysis prior to their revision, and then obtain their implant after they've had their surgery. So. And it's exactly the path that we hope to go down.
Great. Now from Andrew Cuff. So are your MATLAB scripts for converting OpenSim data to Abacus INP files openly available for use by anyone wanting to follow your methodology?
So they are not currently available. This is Alessandro. They are not currently available, but I guess that we are obviously open to sharing this data, and so I suggest that if you are interested, you can contact us, and we can take a look into what we can share with you guys.
Great. Now from Danilo Catelli. For the lunge task, where you're getting pretty deep knee flexion, did you find any problems with muscles crossing the bones? If you did you add additional wrapping surfaces, or how did you handle that?
This is AZ. In the models, in the final models that I had created, the only muscles that I had represented were the quadriceps. And contact there was defined with the implant component, and the patellofemoral soft tissue wrapped around the patellar component and the insert, if necessary. But any other wrapping with the bone was not modeled. And so if other structures such as hamstrings in the future are included, then we have created models in which we've included analytical surfaces to represent the wrapping of those structures. But in the simulations that I had described for that last study, contact between that patellofemoral soft tissue was with the implant components only.
Okay, great. Now from Mitchell Wheatley. In the FEA model with the soft tissue, it looked as if shell elements and bar elements were used. Is that the case, and what was the reasoning for those modeling choices?
Yeah, the patellofemoral ligament and the quadriceps mechanism were modeled with membrane elements, and they were embedded with springs, and that development of that structure had been validated in previous cadaveric work that we've used. But we used membrane elements because they carry load in the axial direction only, and they don't carry any load in bending.
Okay, thanks for clarifying. I have to say that you guys are setting the record for the number of questions that people are asking. So people are really interested and engaged. So that's awesome. We'll have time to get to a couple more, and then the others will forward so we can put them up on the webinar page. So this is from Amit Iyengar. What were the challenges in integrating the X-ray kinematics with the motion capture kinematics?
That's a good question. Most of the challenge just is in time synchrony, just synchronizing the two systems. So it's really a technical challenge that we had to resolve. And then there's also some resolution of coordinate systems as well to make sure that what we're basically we use a neutral pose, the same as you might in traditional or conventional motion capture, so that we're starting the radiography system as well as the motion capture system from the same pose.
Okay. So we'll have one final question. This is from John O'Connor. He says, very interesting and insightful talk. Do you think it's important to model the muscle weakness that can be common in osteoarthritic patients in OpenSim or when you're computing the muscle forces?
Yes, I think that's important. And so one of the things that we didn't show here that in most of our analyses we do is we also collect strength information from all of our subjects using a Cybex dynamometer, and we scale our OpenSim models to their strength. And and I think as was shown in AZ's results, the whether his changes in like the knee longevity when he was showing knee torque, and there was differences between film and anatomic. It shows that that basically quadriceps efficiency or differences in quadriceps force or strength can definitely make a difference in how people perform the task, how it's simulated.
Great. Okay, so we'll have to go ahead and wrap up the Q&A session. But as I said, we'll send all the questions over to the speakers so they have a chance to respond to the questions we didn't get to. If you guys could help me flip through the last couple slides in the slide deck.
Okay, go to the next one.
We might, let's see, one more. We took care of questions. I really want to say again, thank you, Kevin, Alessandro, and AZ for the great talk and being part of the webinar series and sharing your work. I also want to acknowledge our funding sources. The OpenSim and the webinar series are supported by several grants from the NIH, including the NIH grant that funds our National Center for Simulation and Rehab Research. One more slide. Thank you again, everyone, for a great discussion. You can get more information about the NCSRR and the OpenSim project. You can learn about upcoming events and other resources from the OpenSim community at our website. And then also we ask that you complete the survey that's going to appear in a pop-up window at the conclusion of the webinar. This will help us improve the webinar series and choose upcoming topics. So thank you again, everyone, for participating and setting a record, I think, for a number of questions and a really interesting discussion. We hope you'll all continue to stay involved with OpenSim. Thanks, everyone.